What if the first real photograph of another planet turned out to be a picture of something that should not even exist? Somewhere out there, a telescope pointed its enormous mirror at a tiny speck of light circling a distant star, and what came back made scientists go quiet for a moment before they all started talking at once. Before we go any further, hit that like button right now, tap subscribe, and send this to one person who still thinks space is boring, because after this video, they never will again. For a very long time, seeing another planet directly was almost a fantasy reserved for science fiction. Astronomers could detect planets indirectly. They could measure the tiny wobble a planet causes in its star's motion. They could watch a planet's shadow dim a star's light for a few hours as it passed in front. But actually seeing one, the way you'd see a photograph of Mars or Jupiter through a lens, that was an entirely different challenge. A planet is small, cold, and dark compared to the blazing star it orbits. Trying to spot it directly is like trying to see a single firefly sitting 1 inch from a lighthouse beam, from miles away at night through thick fog. That is exactly why what the James Webb Space Telescope managed to do felt like such a turning point. It did not simply detect a planet through indirect clues buried in data. It captured actual light that traveled directly from the planet itself, across trillions of kilometers of empty space, straight into its mirror. A real image, a real world, sitting quietly in the dark, orbiting a star that is not our sun. To pull this off, engineers had to solve a problem that had frustrated astronomers for generations. Webb carries a mirror over 6 meters wide, built from 18 gold-coated hexagon panels that folded up like origami for launch and slowly unfurled once the telescope reached its final position in space. But the mirror alone was never going to be enough on its own. Webb also relies on specialized instruments called coronagraphs, small disks and masks designed to physically block out the blinding light pouring from a star, so that the much fainter light bouncing off a nearby planet can finally slip through and reach the detectors. Think of it as holding your thumb up in front of the sun so you can finally make out the silhouette of a bird flying nearby. That is roughly the idea behind Webb's design, except carried out with a level of precision that borders on unbelievable. Earlier telescopes had tried this exact approach before and mostly failed, or managed only the faintest, blurriest hints of a shape. Every attempt before Webb ran into the same wall. The star's glare simply overwhelmed everything else nearby, turning any hope of a clean planetary image into a smudge lost in noise. Webb was the first instrument sensitive enough and precise enough to actually push past that wall on close to its very first serious attempt. When the data finally came back and the image resolved into something clear, scientists were not simply looking at a dot on a screen. They were looking at proof. Proof that a planet sitting an almost unimaginable distance away could be seen and studied directly, not just guessed at through shadows, wobbles, and secondhand calculations. But here is where the story stops being simple. Because the more Webb looked, the stranger everything got. Some planets turned out to be sitting in places where our own theories say planets should not be able to form at all. Some planets carried chemical signatures that, here on Earth, only ever come from living things. And one planet in particular has scientists choosing their words with unusual care, because they know exactly how big a claim they would be making if they said the obvious thing out loud. Let's start with a planet that quietly became the center of a genuine global argument among scientists. It is called K2-18b, and for a while, it was treated as just another entry on a long, growing list of distant worlds. Bigger than Earth, smaller than Neptune, sitting far enough from its small red star that liquid water could, in theory, survive somewhere on or above its surface. Nothing about it screamed for attention at first. Then Webb turned its instruments toward it, and everything changed almost immediately. Instead of a blurry, uncertain guess pieced together from limited data, Webb delivered a detailed breakdown of the planet's atmosphere, layer by layer. It found water vapor first. That alone was exciting, but not entirely shocking on its own. Then it found methane, then carbon dioxide. Piece by piece, scientists began assembling a picture of a planet wrapped in a thick hydrogen atmosphere, sitting above what might be a deep, dark planet-wide ocean stretching far beneath the clouds. And then came the detail that changed the tone of the entire scientific conversation. Webb picked up faint traces of a molecule called dimethyl sulfide. Here on Earth, this specific molecule is almost always produced by living organisms, mostly tiny marine life drifting through our oceans. It is actually one of the reasons the open sea has the particular smell that it does. Finding even a hint of it on a planet light years away is not something careful scientists say lightly, and it certainly is not something they announce without hesitation. To be completely clear, nobody stood up at a podium and declared that aliens had been found. Scientists are careful people, and rightly so. They know nature can sometimes produce the same molecules through purely chemical non-living processes we simply have not fully mapped out yet, especially under conditions we have never directly observed before. So research teams went straight to work trying to explain the signal away, using ordinary chemistry alone. They examined strange volcanic activity as a possibility. They looked into unusual mineral reactions involving trace elements. They considered every non-living explanation they could reasonably think of. But here's the strange part nobody expected going in. Every single non-biological explanation researchers tried required stacking one unlikely coincidence on top of another just to make the numbers fit. Meanwhile, the simplest explanation, some kind of biological process at work, kept matching the data more naturally and more consistently than any of the increasingly complicated alternatives being proposed. That does not prove life exists there. It genuinely does not. But it does mean that, for the first time in this kind of search, the boring explanation has become the complicated one, and the complicated explanation has quietly become the simple one. That alone should tell you how unusual this particular moment in science really is. There's another angle worth sitting with here too. K2-18b belongs to a category some scientists now call Hycean worlds, planets covered in vast oceans and wrapped in thick hydrogen skies, quite unlike anything sitting in our own solar system. Before Webb, this entire category was mostly theoretical, a shape on a whiteboard rather than a confirmed reality. Now there's a real candidate sitting right in front of us, and that alone forces astronomers to widen the entire search for habitable worlds beyond the narrow Earth-shaped box we used to search within. Maybe the next home for life doesn't look like Earth at all. Maybe it looks like a planet-sized ocean sealed beneath a thick, hazy sky, quietly waiting for the right instrument to finally notice it. If you're starting to feel that itch of curiosity, that little voice in the back of your head asking, wait, what else did they find? Good. Hold on to that feeling, because it only gets stranger from here. Now let's talk about a planet that broke the rule book in a completely different way. This one is called HIP 65426b, a giant roughly 7 times the mass of Jupiter. On its own, a large gas giant is not particularly surprising. Webb has studied plenty of those already. What is surprising here is exactly where this one happens to be sitting. According to everything astronomers currently understand about how planets form, giant planets are supposed to grow inside the thick disk of leftover gas and dust that surrounds a young, newly formed star. That disk has to be dense enough, close enough, and rich enough in raw material to slowly build something this massive over time. But HIP 65426b sits so far out from its own star that the disk in that particular region should have been far too thin, far too spread out, to ever assemble a planet this size through any conventional, gradual process. So how did it actually get there? Nobody knows for certain, and that uncertainty is exactly what makes this particular planet so fascinating to study. One idea suggests the planet originally formed much closer to its star, and was later flung outward during some chaotic gravitational tug-of-war with other massive objects in its early system. Another idea is stranger still. Maybe this planet never formed around this star at all. Maybe it began life as a rogue world, drifting alone through freezing interstellar darkness for millions of years after forming somewhere else entirely, until it finally wandered close enough for this particular star's gravity to catch it and quietly pull it into a permanent orbit. Some researchers have started calling planets like this one-orphan giants, worlds that appear to have been adopted by a star system rather than genuinely born into it. If that particular idea holds up under further study, it would mean our galaxy could be quietly full of enormous planets drifting between star systems, occasionally getting captured, completely rewriting the tidy, orderly picture we once had of how solar systems are supposed to come together. When Webb studied the light coming directly from this planet's atmosphere, things got even messier still. Instead of a smooth, predictable chemical signature you'd expect from an ordinary gas giant, it revealed strange layering, unexpected temperature shifts, and cloud patterns that simply did not behave the way a calm, long-settled atmosphere should. It looked less like a planet that had quietly grown up in one place for its entire existence, and more like a planet that had actually been through something. Some kind of violent past, some kind of long, strange journey across space, written directly into the chemistry of its own sky. To understand just how significant this is, compare it to our own solar system for a moment. Every planet here formed roughly in the region where we still find it today, following a fairly orderly pattern. Rocky worlds close to the sun, gas giants much further out. HIP 65426. B throws that entire tidy pattern into question. If planets this massive can end up this far from their star, then our neat mental model of planetary systems might only describe one narrow possibility, out of a much wider, messier range of outcomes playing out across the galaxy. And this isn't just an academic curiosity either. If orphan giants like this one really are common, it changes how astronomers plan future searches entirely. Instead of only scanning the tight, familiar zones close to a star where planets are expected to form, telescopes might need to scan much wider fields, looking for faint, drifting worlds sitting far outside the regions anyone previously thought to check. That's a genuinely bigger, more expensive kind of search, but HIP 65426b is exactly the kind of discovery that convinces funding committees it's worth doing. Now, if giant orphan planets floating between stars already sound wild, wait until you hear what happened. When Webb finally turned toward the planet, almost everyone wanted to see the most. If you've made it this far, you clearly care about where this is going, so let's make it official. Type the word Webb in the comments right now if you want part 2 of discoveries like this, because your comment genuinely tells the algorithm to show this video to more people who need to see it. Proxima b sits closer to us than almost any other known exoplanet, just over 4 light years away, orbiting the very nearest star to our own sun. For years, it has been the planet people dream about visiting first, if humanity ever manages to build anything capable of true interstellar travel. It sits comfortably inside the habitable zone of its star, meaning temperatures there could, in theory, allow liquid water to exist somewhere on its surface. So naturally, everyone wanted Webb to point directly at it and finally settle the question once and for all. But this is exactly where the story turns frustrating instead of thrilling. Proxima b orbits so close to its small host star that the glare completely overwhelms any attempt to separate the planet's faint reflected light from the star's blinding radiation. Current instruments, even something as remarkably powerful as Webb, simply cannot cut through that particular glare cleanly enough just yet. On top of that technical problem, the star itself is something of a troublemaker. It is a red dwarf, and red dwarfs are notorious for throwing out sudden, violent solar flares, bursts of radiation strong enough to strip an entire planet's atmosphere away completely if they happen often over billions of years. If Proxima b ever had oceans, or any kind of breathable sky at all, there is a real, serious chance those relentless flares tore it all away a very long time ago. There is also a decent chance the planet is tidally locked to its star, meaning one side always faces the star in permanent, unbroken daylight, while the opposite side sits trapped in permanent darkness, with only a thin strip of twilight in between where conditions might land somewhere genuinely livable. It is close enough to dream about constantly, yet still too bright, too dangerous, and too technically difficult to properly study with anything we currently have available. That contradiction, the single nearest planet to us being one of the hardest worlds to actually understand in detail, is honestly one of the more humbling lessons Webb has run into so far in its mission. It is a quiet reminder that raw distance is not always the biggest obstacle standing in the way of this search. Sometimes the biggest obstacle is simply the overwhelming glare of the very star that makes a planet's existence possible in the first place. Engineers working on future telescope concepts have already pointed to Proxima b directly as one of the key reasons for building even more advanced starlight blocking technology down the road. This is actually why space agencies are already designing Webb's eventual successor, a mission sometimes called the Habitable Worlds Observatory, built specifically to solve this exact glare problem once and for all. The goal is a telescope precise enough to block a star's light almost completely, leaving nothing but the faint, clean glow of a nearby planet behind. If that mission succeeds, worlds like Proxima b, currently stuck just out of reach, could finally become fully readable, atmosphere and all. In a strange way, Proxima b's silence right now isn't a dead end. It's a blueprint for exactly what needs to be built next. Let's move now to a planet that turned out to be one giant boiling chemistry laboratory. WASP-39b is what astronomers call a hot Jupiter, a massive gas giant sitting so close to its star that its atmosphere is constantly being cooked, stretched, and stripped away by intense heat. Nobody expected much complexity from a planet like this going in. Extreme, relentless heat usually suggests a fairly simple, predictable atmosphere with little going on beneath the surface. Instead, Webb uncovered one of the most chemically rich atmospheres ever properly recorded on any exoplanet studied so far. Its skies contain water vapor, sodium, potassium, carbon monoxide, methane, and a molecule called sulfur dioxide, which only forms when intense starlight triggers very specific chemical reactions high up in a planet's atmosphere. This marked the first time scientists had ever directly observed this exact kind of chemical process, known as photochemistry, actually happening in real time, on a world entirely outside our own solar system. Here on Earth, remarkably similar chemical reactions helped build our own protective ozone layer over the course of billions of years. Watching something comparable unfold on a planet hot enough to melt metal tells researchers that this kind of active atmospheric chemistry is not some rare, delicate accident unique to Earth's particular conditions. It might instead be a fairly normal, widespread process happening across all kinds of planets scattered throughout the galaxy, even ones that look completely hostile and lifeless at first glance. That single discovery quietly expanded the entire scope of what's worth searching for going forward. Planets that once looked like nothing more than furnaces, barely worth a second glance from anyone, might actually be busy, chemically active places genuinely worth studying far more closely than anyone had previously assumed. It reshaped, in a small but meaningful way, how astronomers now decide where to point this telescope next. What makes WASP-39b even more valuable is that it gave researchers something they had never really had before, a real working test case. For years, scientists built computer models predicting how starlight should react with different gases high in a planet's atmosphere. Those models were mostly theoretical, built on assumptions rather than direct observation. WASP-39b let researchers finally check their math against reality, and in several places, reality didn't quite match the models. Some of the predicted chemical ratios were off. Some reactions happened faster or slower than expected. That kind of mismatch might sound like a failure, but in science, it's actually a gift. It tells researchers exactly where their understanding is incomplete, and exactly where to focus the next round of study. Now let's talk about the system that broke a lot of hearts, in the best possible scientific sense. TRAPPIST-1 is a system built around 7 Earth-sized planets, all circling one small, cool star, several of them sitting comfortably inside the habitable zone. For years, it was treated as the closest thing we had ever found to a genuine miniature version of our own solar system, and plenty of people quietly hoped Webb would eventually uncover clear signs of life somewhere within it. When Webb finally examined the 2 innermost planets in that system closely, the results were not what anyone had been hoping for. There was no meaningful atmosphere present on either world. No thick blanket of surrounding gas, not even a thin, wispy layer clinging faintly to the surface. Just bare, exposed rock, constantly hammered by radiation pouring out from their small, aggressive host star. Without any atmosphere at all, a planet cannot properly hold onto heat, cannot shield itself from harmful radiation, and cannot sustain the basic underlying chemistry life genuinely depends on to get started. The excitement that had steadily built up for years around this entire system deflated almost overnight once this particular data came back. A system once widely treated as a likely galactic oasis turned out, at least for these 2 inner worlds, to be closer to a genuine dead end. But even a disappointment like this taught scientists something quietly valuable. Habitability is rarer and considerably more fragile than we had assumed. A planet can check nearly every box on paper, the right size, the right distance from its star, the right general temperature range, and still turn out to be completely lifeless once you actually look closely enough. The remaining outer planets in that system haven't been fully studied in detail yet, so the door isn't completely shut. But the underlying lessons stuck firmly with the entire scientific community. Looking perfect from a distance and actually being livable up close turn out to be 2 very different things entirely. Put all of these discoveries side by side now, and a strange, unmistakable pattern starts to emerge. Webb has found a possible ocean hidden beneath a thick hydrogen sky, a giant planet sitting in a place where physics says it shouldn't be able to exist, a nearby planet permanently hiding behind the blinding glare of its own host star, an atmosphere behaving like an active, ongoing chemistry experiment, and an entire system that looked perfect on paper but turned out almost completely empty once examined up close. Everywhere Webb looks, it keeps finding planets, storms, oceans, and strange, unfamiliar chemistry, almost everything you'd expect a living world to need in order to get started. And yet, so far, not one single confirmed sign of actual life has turned up anywhere. Statistically speaking, that silence genuinely feels wrong to sit with. With this many planets, this much water, and this much organic chemistry scattered throughout the galaxy, life should, in theory, be turning up somewhere by now, at least according to simple probability. Some scientists genuinely believe life is incredibly rare, an unlikely spark that almost never manages to properly catch, even when every other necessary ingredient happens to be sitting right there, ready and waiting. Others believe our instruments, as remarkably advanced as they already are, still simply are not sensitive enough yet to catch the specific faint signals that would actually confirm it one way or the other. And some researchers quietly wonder if Earth itself was simply lucky, a planet that happened to line up an unusually long, fragile chain of coincidences that most other worlds in the galaxy never get the chance to line up at all. Some researchers have started calling this contradiction the Great Silence, the strange gap between how common the raw ingredients for life appear to be, scattered generously across the galaxy, and how completely absent any confirmed sign of actual biology remains in every single world studied closely enough so far. It raises an uncomfortable possibility that scientists are only now starting to take seriously, that the leap from simple chemistry to genuine self-sustaining life might be a far rarer, far more delicate event than almost anyone previously assumed, even when every other condition appears to line up perfectly in a planet's favor. It also raises the flip side of that same question, one worth sitting with for a moment. Maybe Earth itself is less of a typical outcome and more of a genuine outlier, a planet whose specific path to life depended on a longer, more fragile sequence of fortunate accidents than we ever gave it credit for. That would not mean life is impossible elsewhere in the galaxy. It would simply mean Earth's own particular success story might be considerably harder to repeat than the sheer number of promising-looking planets out there would suggest at first glance. Nobody knows for certain which of these possibilities is true yet. But that is exactly what makes this particular moment in science so genuinely exciting to be alive for. We are no longer simply guessing about these distant worlds from a comfortable distance. We are now reading their actual chemistry directly, molecule by molecule, the same way you might read the ingredients label on something sitting right in front of you. Except the object in question happens to be sitting trillions of kilometers away, and the light left its planet long before most of us were even born. Quick pause before we land this. If you've stuck around this long, you're clearly the kind of person who actually cares about real discoveries instead of empty hype. So do us one favor, ring the notification bell so you catch the next deep dive the moment it goes live, because we've got several more strange worlds already lined up. Every new image, every new atmospheric reading, every strange, unexpected signal Webb sends back brings us one step closer to answering a question humans have been quietly asking for as long as we've been able to look up at the night sky. Are we truly alone out here? Nobody can honestly answer that yet, and it might be years, maybe decades, before anyone actually can. But for the very first time in human history, we finally have a tool genuinely capable of going out and looking for that answer, instead of simply sitting back and wondering about it from afar. Think about what that actually means for a moment. A machine sitting roughly 1 million miles from Earth, quietly staring at a point of light for hours at a time, is now able to read the honest chemical fingerprint of a world so distant that its light left the surface long before most of us were even born. By the time that light finally reaches Webb's mirror, it carries within it an unfiltered snapshot of conditions on a planet most of us will only ever know through data rather than direct experience. There is something genuinely humbling in that thought, and something quietly thrilling about it too. Somewhere out there, right now, while you're watching this, Webb is quietly staring at another distant star, patiently gathering light that has been traveling toward us for years, sometimes centuries, carrying inside it the honest chemical fingerprint of a world we may never physically visit ourselves. One day, one single image, one single reading, might finally give us the answer humanity has been chasing since the very first person looked up at the night sky and quietly wondered if anyone out there might be looking back. And when that day finally comes, whenever it comes, you'll be able to say you were paying attention long before the headlines ever caught up. Not because you read a single flashy headline for 3 seconds and scrolled past it, but because you actually sat here and walked through what each molecule meant, what each strange orbit revealed, and why some of these discoveries excited scientists while others quietly broke their hearts. That kind of understanding is rare, and it's exactly the kind of depth we plan on bringing you every single time Webb finds something new, because this is genuinely only the beginning. Webb still has years left in its mission, and every single month it turns towards stars nobody has properly studied yet. Star systems that might be hiding worlds even stranger than everything we just walked through together. Somewhere out there could be a planet with weather patterns unlike anything on Earth, an ocean world with a completely different chemistry than K218b, or a signal so unmistakably biological that even the most cautious scientist alive would struggle to explain it away. We simply don't know yet. And that uncertainty, that not knowing, is exactly what makes this the most thrilling era exoplanet science has ever seen. So before you go, do one last thing. Share this with someone who needs a reminder that the universe is bigger, stranger, and far more alive with possibility than anything we ever imagined, because, trust me, plenty of people still haven't heard a single word of this story yet.